Hello and welcome back to Calculus 1 section 4.2 part 2, which is the second derivative test. So the first derivative test was utilizing the first derivative to talk about increasing and decreasing portions of a function. Now we are going to use the second derivative test to talk about concavity. Concavity is the way the line curves. So before I write any definitions or anything, I need to talk about concavity. So concavity is this. I have graphs for you to consider. So consider a piece of a graph that looks like this, and consider the piece of graph that looks like this. Now you see, would you agree that both are increasing?
Yeah.
Right? Yes. So now this one is concave down, and this one is concave up. You see, concave up looks like U, and concave down is inverted U. So I say hold the water, spills the water, right? Now, if you observe, concave up type of a graph has both decrease and increase at the same time, right? So I just wanted to show you that if you look at the pieces of the graph that I provided in the blue example, they're both increasing, and one is concave up, concave down. If you look at the green ones, which give the complete picture of concave up and concave down, you see that both contains increasing and decreasing pieces. So we are either going to have the entire U shape to consider, or we're going to have these pieces. So the best one to just think about concavity a little bit would be 1 over x. This is y equal 1 over x. And what you see over here is that this piece is decreasing, and it's concave up or down. Yeah. Very good, concave down. Why is it concave down? Because if I am to complete the shape, it would be spilling the water, right? And then you have on the other side that the piece is also decreasing, right? Is it concave up or down? Up. So concave up. I think my battery is dying over here, so. No, there is one in my bag. It's just I need to go all the way there and get it. So now we can go and talk about the second derivative test. So here is the second derivative test. It simply says if the second derivative at a is less than 0 on some interval I, f of x is concave down. F of x is concave down on that interval I. And the second part, if second derivative is larger than 0 on I, function is concave up on that interval I. So that's it. You see that it's absolutely the same stuff, looks the same as the increase decrease. Yes?
So in a sense it loops back to be somewhat close to x squared, where if it's a positive x squared, it's up, and if it's a negative x squared, it's pointing down, where if the second derivative is positive, it opens up in a sense.
Yeah. Mm-hmm. So now the procedure for this, and let's use well, x squared is actually in this case too trivial, so let's use 1 over x for the example. So if I use 1 over x, we need to find second derivative. Actually, no, it's bad to do this. Let's not use that one because other stuff. Let's just use a polynomial. How about x cubed minus 9? Well, so x cubed minus 9. So what do I have? I have the first derivative, which we are not going to need for calculations, 3x squared. And then I have a second derivative, which is 6x, and we set that one equal to 0, because now we're working on a second derivative test. So when I set that equal to 0, I get x equal to 0. This is called an inflection point. And the inflection point is the point where concavity changes. So change in concavity. So what is your min and a max? Min and max gave you change in increase, decrease. Inflection point gives you the change in concavity. So you see it's the same structure, same steps. It's just a different concept because we are using the second derivative. So now here it is, second derivative test. You partition and we have only 0. Our domain is negative infinity to positive infinity. We pick 2 test points. Again, pick these guys, doesn't matter. And then we do our f double prime at -1 is 6 times -1, -6, which is less than 0, which means concave down. And second derivative of 1, which is 6 times 1, which is 6, which is larger than 0, concave up. So if you look at this, we know that concavity to the left of 0 is concave down, CD, and to the right is concave up. Now if you look at the graph of x cubed minus 9, it's just an x cubed graph that goes through the -9. It's a x cubed graph which is shifted down. Now, do you see how concavity actually changes at that point 0, -9? 0, -9 inflection? You see, on the left, you have, you can complete, and it looks like concave up. So this piece here is concave up, and we see that to the right of 0 is concave up. And then the one on the left, you can complete like this, it's concave down, right? So it's very straightforward, in my opinion, on how this thing works. We can check good old y equal e to the 3x. The first derivative is 3e to the 3x. The second derivative is 9e to the 3x. And when you set that equal to 0, what do you get? You get no solution, right? Which means no inflection points. We have no vertical asymptote to partition either, but for the second derivative test, you can use the entire domain as partition and just pick a test point. We are obviously going to pick 0 as a test point, and when you use the test, second derivative at 0 is going to be 9e to the 0, which is 9 larger than 0, concave up. The entire function is concave up. Now, if you are to actually look at the graph, the graph looks like this, and it's clearly concave up, right? So this obviously works 100% of the time. It's very systematic, and the calculations are identical to your first derivative test, except now you're using second derivative, and instead of getting increase decrease, now you are getting concavity, so concave up or concave down. So now I would like to challenge you to complete 1 over x. your partitioning is happening on critical, or not critical points, the inflection points, or at vertical asymptotes. So find the second derivative and see if so find the second derivative, set it equal to 0, see if you can get anything out of it. So if I set the second derivative equal to 0, do we get inflection points? No. So no solution, which means no inflection points, IP, whatever. We do have vertical asymptote, so second derivative test, we are going to partition on 0 from negative infinity to infinity and use test points -1 and 1. So second derivative test, so second derivative at -1 is going to be 2 over -1 cubed, which is -2 less than 0, concave down. Second derivative at 1 is 2 over 1 cubed, which is 2, which is larger than 0, so concave up. And now if you want to check, you know how the basic graph looks like. So if you look at the cube, the 1 over x graph, you see that this is concave down, you see that this is concave up, and you know the vertical asymptote right in the middle at 0. So partitioning went well, and that's it. I hope you're not disappointed, but procedures for both are the same. You just have to be careful which concepts you get out of each of the procedure. So the first derivative is related to critical points, it's related to min and max, it's related to increase and decrease. Second derivative has the inflection points, and it talks about concave up and concave down. And that's it. So you should try homework examples, and tomorrow we might take a look. If you have homework question, we'll take a look at that, and we are pushing on to do 4-3 and at least start 4-4. I don't think we can finish 4-4. It's another batch of word problems on optimization, so min and max. So I will see you all tomorrow.